Yeah, so today I will talk about local synaptic update rule for ICA and dimensionality reduction. Okay, so Darwin's evolutionary theorem is a powerful theorem in biology. It explains such a diversity of organisms in terms of their effort to adapt to their environment and for their survival. And what the learning does in the brain is in a sense similar, despite at very different timescales. What the brain does is that neural circuits adapt to their own environment by changing synapses in their lifetime. So I'm hoping that a relatively simple principle can explain seemingly diverse brain circuits in the brain. And the two general questions that I would like to ask are how neural networks in the brain adapt to the environment, and what is the, following Darwinian theorem, what is the optimization principle for describing this process? So what's important in this kind of thinking is what is the cost function or what is the utility function. Simple enough to work on and give interesting predictions. In 1988, Ralph Rinsker came up with a proposal. Maybe synaptic plasticity rule can be derived from maximization of information transmission. After all, brain is an information processing device, so if neurons cannot transmit information, that's useless. So to the first order, let's think about information maximization from a bunch of presynaptic neurons to a postsynaptic neuron. And the synaptic change may be described so that this information transfer is maximized. Some long time ago, I computed this Infomax learning rule for spiking neurons and found some interesting features. Basically, what I computed is mutual information from the presynaptic inputs to the postsynaptic output, and derived the gradient ascent learning rule for synapses to maximize that quantity. And here's the theoretical prediction. The learning rule says that synapse must change when a neuron receives its presynaptic input. Upon the receival of presynaptic spike, the weight should be changed according to postsynaptic firing probability or firing rate. So let's look at this green curve. When
Can you say what the input and the output were that you were trying to calculate the mutual information?
Well, that depends on, it's an online learning rule. So
What is it trying to learn?
the mutual information between presynaptic input spikes and output spikes.
Of those presynaptic, how did you model that?
Those are basically point process or 0-1 binary sequence.
Just independent random Poisson process.
Well, the statistics must be learned. So it's an online learning rule. Given 0 and 1s of input, it must compute on average the mutual information. So the output neuron is a Poisson neuron. Input is not explicitly parameterized. You give some input statistics, and output is just Poisson neurons, and you compute the mutual information. Luckily,
For your learning rule, what was the ensemble from which you assume the inputs are drawn?
it's empirical, so it's based on samples. So you can just maximize something like this is mutual information, and this is the average. You can compute the gradient. Again, of this I, and it's essentially like again so on average this will maximize information, but this one is the update.
My question is simpler than that. What is P of X when you are calculating this curve?
Well, we don't need to assume. We just compute this quantity as a delta W over X and Y, and we need to average this over X and Y.
Yes, so what was P of X when you averaged?
For this one, just Poisson input spike trains, but in the next slide, I will take a, yeah.
These curves are drawn for P of X, that's the
Poisson input spike, yeah. But it doesn't have to be Poisson, that's what I'm saying.
No, but these curves are for Poisson. Or does it change if you assume, I assume that if your inputs are all highly correlated, that we will get a different curve.
Well, this one doesn't assume any probability distribution, right?
Yeah, but the average
does. Average does. But I'm talking about the update as a function of X and Y, and the X can be anything. Yeah, so it's a bit detailed, but anyhow, let's look at this green curve. You should change the synapse upon the receival of input. When the output firing rate is high, potentiate the synapses. Output firing rate is low, depress the synapses. But this optimization has to be done within the energy budget limitation. So if the spike is, background spiking rate is too high, energy is running out. So with too high background firing rate, there is a bigger area of depression of synapses. If the background activity is too low, there's a lot of budget left, so it can potentiate additional synapses. So it also depends on the constraint, and this theoretically derived learning rule has some similarities with the experimental observations. Here it's a in vitro experiment. They cut the slice from the visual cortex of rat, and when the slice is prepared from a normal rat, then this is a curve. But when the slice is taken from visual cortex of dark-reared animal, then the curve is shifted, like a shift from this green curve to blue curve. So information maximization can tell some interesting feature of real plasticity rules. This is another demonstration. Given the pre-post spike trains or post-pre spike trains, there's another update for synapses, optimal update for synapses. Basically, it says, if pre comes before postsynaptic spike, it can transmit information. So those are useful presynaptic input. If the presynaptic spike comes right after the postsynaptic spike, then due to refractoriness and channel desensitization, information cannot be transmitted well. So let's depress that kind of synapses. Because they are metabolically costly and the cost is proportional to the synaptic strength, whereas for big synapses, the utility of information is not proportional to the synaptic strength. So it gives a STDP relationship as well as weight dependency for the STDP. So that's what I did long time ago. But when we think about information maximization in a more realistic environment, there is not only one postsynaptic neuron, but there are multiple neurons coherently encoding the information. And this is Infomax in this setup is a more difficult problem because coordination among output neurons is required. Luckily, we know the mathematical expression, what is the solution and what's the learning rule. In this case as well, the information transfer is maximized in the presence of small noise when these individual postsynaptic neurons encode independent features. And Beer and Senosky derived a learning rule to achieve that independent representation. This is called ICA, independent component analysis learning rule. But the problem is that this is so-called non-local learning rule. It involves the matrix inversion and then transpose. And so this means that if you want to change this synapse here, to compute the change, it needs to know the weight of non-connected other neurons. So the learning rule is called non-local. And how biological neurons implement such learning rule was unknown. We've recently come up with a approximation of Beer and Senosky's learning rule. It's called, we named the error-gated Hebbian rule. It's basically an approximation of this learning rule, and we get this simpler expression. Right at the solution, independent solution, we can formally derive from here to here by integration by part. But around the ICA solution, these updates are similar, and in fact, the difference is negligible up to the second order expansion of the deviation from the solution. So this is a reasonable approximation of Beer and Senosky's rule, and it has some nice properties that I will explain next. So in the learning rule that we derived, the change in synaptic weight is described by a product of three factors. X is a presynaptic activity, G of U is a postsynaptic activity, so X times G of U is a typical Hebbian plasticity rule. But it also has an additional third factor, E, which is a scalar common to all synapses. This is a global scalar factor, possibly implemented by GABA release or neuromodulator or glial factors. What this global scalar factor does is the following. When it depends on the activity level of surrounding neurons, if the surrounding output neurons have a small firing rate, small activity level, this E factor takes a positive value, E0. So it implements Hebbian plasticity when surrounding neurons are rather silent. But when the activity of surrounding neurons become high, then this negative part becomes large. Then this sign will become negative, basically implementing anti-Hebbian plasticity, switching the sign. And there is no formal proof this is going on in the brain, but there are circumstantial evidences the polarity of Hebbian plasticity could be flipped by some transmitters. In this case, the experimentalist blocked GABA-A receptors and found that the STDP outcome is flipped from depression to potentiation, potentiation to depression. So in principle, if, let's say, if this GABA-A encodes the level of activity level of surrounding neurons, then this can flip the sign of plasticity from Hebbian to anti-Hebbian plasticity. So it's possible that this could be implemented, and the proposed scheme is something like this, we assume a bunch of sensory neurons, perhaps some representing auditory stimuli, some representing visual stimuli, and so on.
Sorry,
And
what on the switch is due to a change in E0?
change in this one, G is some, let's say, monotonically increasing nonlinearity.
GABA is a global signal.
It's a global signal.
So it should go into E0.
No, the G is the G of UI is the activity of surrounding neuron UI, I, and this is a summation of activity from all surrounding neurons. Okay. E0 is just a positive constant. If the activity level of surrounding nonlinear sum of other neurons increase, then.
So no, what I'm saying is, say this GABA inhibition should be a factor that comes into some of this somewhere in this equation. So it should come in the G.
The sum of G's. Sum of G could be inhibition. Could be.
Yeah, so the G should also depend on inhibition, on this GABA factor, this global factor.
So what I'm saying is G of UI is the activity of neuron I, excitatory neuron I, and inhibition might be equal to the sum of activities.
This is clear.
Yeah.
This is clear. So what I'm just saying that this means that the G should depend on this inhibition, on this global factor. Each. Okay.
It's maybe not. The inhibitory neuron can sum activity levels of surrounding excitatory neurons. This may be G of 1, G of 2, and this may be the sum over GI. The activity of inhibitory neuron may be a sum of surrounding excitatory neurons.
Yeah, my question is simple. So here essentially you are changing an external parameter in these two experiments. Right?
Yeah.
So I'm just asking, where does this external parameter would enter into that equation?
Let's call this sum E1. E1 can be inhibition.
Okay.
Yeah. Okay, so what I wanted to say, those output neurons, some integrate information from different senses, and a global factor E is a nonlinearly sum the activity of the surrounding neurons. This may be inhibitory neurons, and this inhibitory signal or neuromodulatory signal can change the plasticity rule from Hebbian plasticity to anti-Hebbian plasticity.
What was so the experiment was in culture?
This is in ex vivo.
Ex vivo.
Yeah.
And so they added GABA.
They put GABA blocker. Yeah. So how the learning rule behaves? So we assume this is a synthetic example. We just prepared the 3 natural images and 1 noise image. And this is the hypothetical input produced by just randomly mixing these 4 images. And we assume that a neural network receives these mixed images. And so basically these synaptic weights from input to the output are learning by the learning rule that I introduced to you using a global factor E. So here the neuron scan the inputs in time like this. So this corresponds to different times. And after learning, neurons can extract those separate approximately independent images well. So this can work, separating hidden sources. And so the
Can you go back? So you're showing the images sequentially, and then you have basically some nonlinear function.
Yes.
So it's just a standard feed-forward network.
Yes, it's a feed-forward network.
And the output is a threshold linear, or what is that?
Output is sigmoid-like neurons. Yeah.
And then you have this feedback ether.
Yeah. It's not sigmoid. I mean, it's. Sigmoid is okay, but let me see. It depends on the distribution of the source. If basically the optimal nonlinearity is the cumulative distribution of the source distribution, so that works the best. But the fine tuning is not necessary. What's important is if the source distribution is super Gaussian or sub Gaussian. That's the important thing. So that's technical point. Yeah, so it's an interesting possibility if this is realized in the brain, but the point is that the brain maximizes information or learns within the biological constraint, and such biological constraint is also important in a hardware implementation. If we want to design neuromorphic hardware, they need to have similar constraints to the brain. So the application to, let's say, the highly parallel and energy efficient neuromorphic computation can be possible because in the conventional learning rules for ICA, a diagram scheme is something like this. These are different output neurons, and massive communication between output neurons is necessary in a conventional scheme. But in our proposal, all the communication between output neurons is through a scalar factor E. So this can significantly simplify the circuit diagram. And in fact, it was good to know a group from United States implemented our learning rule in the hardware. Despite that the smaller scale now, they reported that despite the hardware limitations, this learning rule can efficiently work. So I've first introduced Berenstenovsky's learning rule, and that learning rule basically computes the inverse of the weight matrix. And for that to be possible, the number of input must be equal to the number of outputs, because it needs to be a square matrix. So in many learning rules, this is assumed that the number of outputs must be equal to the inputs. But our learning rule doesn't have a constraint like this. So you can have fewer number of output neurons than input neurons in our case. And that is an important feature. I now show that this EGHR can be used as a novel dimensionality reduction method in the multi-context ICA problem. So let me introduce multi-context ICA problem. Let's say in the standard setup, still, this, let's say this is a source vector, multiple source vector. And for now, let's assume this is a standard square matrix that mixes the sources. If you receive this as inputs, and the question is how to convert this input to independent sources back again, then the solution is to multiply A inverse here. If you multiply A inverse here, then you'll get the source back. But the multi-context ICA is that this mixing matrix can be context dependent. in a different context, the way of mixing may be different. In that case, at every context, you need to calculate the inverse of A again, and that requires relearning from scratch. We are saying that if high-dimensional inputs is available, then you don't necessarily need to relearn in a new context. So let's assume this is the source and this is a context-dependent mixing matrix, not known to the neural network, but as a context-dependent factor, and we get high-dimensional inputs. Because our learning rule can have fewer number of output neurons than input neurons, it can find the synaptic weights, W, flat and wide matrix, that can separate sources in all contexts from 1 to capital C. If W is designed such that W times this conjunction of the mixing matrix is identity matrix, or it's a permutation and sign flips, then such a solution can separate sources in all contexts. And this is because of the less constraints that EGHR have. It can perform dimensionality reduction by extracting the common sources across the contexts. Let me give one example. In the paper, we generalize it to multiple different examples. Some are more complicated, but this is the simplest situation. There are only 2 contexts, and the red one is one context, blue one is another context. This is the BSS error, blind source separation error, how well the outputs are independent each other. And this is the cost function that our learning rule minimizes, and basically it's similar to BSS error. So upon the first presentation of the context 1 and context 2, neurons learn from scratch what's going on, but after repeated presentation of context 1 and context 2 again and again, then you will find that the error doesn't increase at the transition point. Basically, the network learned a weight matrix that can separate in both contexts well, thanks to the high dimensional input that it receives. So what's effectively happening is summarized here. This synaptic weight matrix has many free parameters because it receives high dimensional input. So upon the receival of the context 1, it has some cost function that has a minimum in some manifold like that. So in context 1, these are the good configuration of synaptic weights. In the context 2, there is another cost function. And along this part, this is the optimal. And if you continue presenting context 1 and switch to context 2, the trajectory follows and converges to those intersection points that satisfies both separation in context 1 and context 2. So without knowing how the sources are mixed in each context, it can reduce the dimensions of high-dimensional input to extract common sources across the context. So this is a novel way to perform dimensionality reduction. And I should just tell that the other learning rules don't instantaneously switch to another context. Some rules need to infer which experts need to be considered at the current context. That requires some time. Some learning rules just emit some useful sources, but also emit 0. So in order to reduce the dimension, additional learning rule should be considered, and that can transiently increase the error. So our learning rule can instantaneously switch to a new context, and that's a useful way to reduce the dimensions. So I've introduced to you that the ICA alone can reduce the dimensions, but the speakers here have already introduced the PCA several times. Principal component analysis is a very useful method to reduce dimensions by neglecting tiny sources. And even this classical method, it's not known how neural networks can implement PCA with a local learning rule. I will explain what kind of learning rule is there in the literature. Oya proposed in '89 a learning rule that extracts principal components. And although this is simple, this learning rule compares the input to back-propagated signal. U is the output signal, and the W is converting the output retrogradiently back to the presynaptic side and computes with the input. So it needs to compute the back-propagated signal from output to the input. And how this is done in the biology is unknown. But again, using the same trick, we can rewrite this equation into a three-factor form where the synaptic weights must be updated with the presynaptic and postsynaptic and global scalar factor. In this case, global scalar factor is a momentarily comparison of the input variance minus the output variance. So with this, we can implement both PCA and ICA in a network just by, let's say, simple superposition, or if the learning rate is slow enough, you can implement, let's say, PCA in daytime, ICA in nighttime, something like this. And by combining them, you can separate sources. Like this is one source.
She was awakened by a shock so sudden and severe that if Dorothy had not.
This is another source, but we also added noise. And this is mixed. And after learning, you can extract.
The author gives some account of himself and family. His first inducements to travel.
All children, except one, grow up. They soon know.
Yeah, so it can do a good job separating sources and neglecting all noisy ones. So that's a useful way to perform dimensionality reduction and separating sources only using local computations. So we think it's a pretty powerful method that the local learning rule can do such things. But at the same time, some people may say these are basically linear methods, linear transformation of the inputs. So if the word is full of nonlinear features, how much applicable it is. So the final part, I would like to tell a little bit into that nonlinear word and say, for some cases, even a linear PCA, ICA can separate nonlinearly mixed sources. But to begin with, it is a difficult problem. Nonlinear ICA is non-trivial because it can have infinitely many spurious solutions. And this is especially true if the neural network becomes complex. Let's say if a deep learning network wants to separate sources, it can add many basis functions, and because of that complexity, it can have infinitely many spurious solutions that are different from the inverse of the generating system. So it's a difficult problem. But fortunately, linear methods like PCA and ICA are not a complex method. So it can at least avoid many spurious solutions. But still a question remains whether PCA and ICA can extract non-linearly mixed sources or not. That is highly non-trivial. But we find yes in some cases if inputs are high dimensional and many sources are almost equally contributing. So we'll talk about nonlinear ICA by dimensionality reduction. So let's assume the system is like this. So this blue part is the generative model. Suppose this is the environment, and the green part is the neural network. This blue part is you have independent sources, and those are projected into high dimensional space by matrix A, and F is a nonlinear function, some nonlinear function, and this nonlinear function is summed by matrix B, and that is this sensory input to a neural network. What a neural network does is simple linear mapping from the input to the output. And the question is, if you perform PCA and ICA as a conversion from input to output, can it retrieve the independent sources? And one important feature is this high dimensionality of this basis function of the input. If the input is very high dimensional, you have many different features. And in this special case, you can basically, we showed that it's possible to extract non-linearly mixed sources. The more technical derivations are here, but let me very intuitively talk how this is possible. First, there are multiple sources, and the contribution of each source is tiny, right? It's one source among many. So contribution of one source is tiny, and that effect is effectively linearized. So you can, if you ask, how much the correlation between a particular source S and output X, then the correlation covariance is basically computed by linearization of this nonlinear function. And another important feature is that this source times the random output is almost uncorrelated. Each element of this AS are almost uncorrelated. Correlation is very small. And using that feature, you can also compute that this input covariance is dominated by a linear component. So this is a linearized component, right? So in this condition, we can compute a linear decoder function, W. This is the optimal linear decoder to extract S from observed X. And that is simply computed like this. The question is, we don't observe S, right? Directly, it's hidden. We only observe X. Can we compute this linear optimal weights. But if this holds, it's actually possible because this covariance of X you can directly observe, and you want to compute this factor, but this factor is basically the half of this input covariance. So if you perform principal component analysis, you can extract these features as a PCA of a major component up to some multiplication of orthogonal matrix. So basically you get this covariance of S and X with a multiplication of orthogonal matrix, which is undetermined. But that orthogonal transformation can be easily found by performing ICA because only one orthogonal transformation gives back independent sources back. Otherwise, it's correlated. So, just by looking at this covariance of X, you can compute this optimal linear decoder, and that can extract non-linearly mixed sources. And here's a numerical simulation. It shows the blind source separation error as a function of learning time step. And it, of course, depends on how many sources are there and how many basis functions are there. But if you have many, many basis functions per source, then as learning goes, then you can separate the sources. And when the condition is met, we can show asymptotically zero error achievable with many sources and many bases per sources. So the final part, we apply this idea to dynamic context. So here we show that even linear method like PCA and ICA is powerful because it can separate even non-linearly mixed sources. And this can be applied to a dynamic condition. Given high-dimensional dynamic inputs, PCA and ICA useful for extracting dynamics of hidden sources, and can they predict their sequence? And basically, we say yes. Predictive PCA, we call it pred PCA, and ICA can identify low-dimensional dynamics of hidden sources and minimize the prediction error. I don't have time to talk about full technical details, but let me give what we did. So the situation we are thinking is we have sequences of sensory inputs coming in. Let's say in case of MNIST digits, in one case, it's an ascending order, 0, 1, 2, 3, 4, 5, 6. There are some random flips time to time, but with a large probability, it's just an ascending order. Or it can be a Fibonacci sequence. Given the past 2 digits, the next one is uniquely determined. So you can, again, add some stochasticity to the sequence, but it's close to deterministic sequence of digit in terms of the number, but the images can be, sometimes weird handwriting letters. Sometimes it's a different handwriting letters. So what this system wants to do is it receives dynamic input digit sequences in time, and the question is whether we can extract the underlying sources. And here, the underlying sources is the concept of 10 digits, right? So what we do is what we call a predictive PCA. What it does is, given the history of sensory inputs, first estimate the most likely next time sequence. This is called AR process. vanilla AR model. But that is not sufficient. AR is not sufficient because it tends to overfit the data. So some compression is useful. So we compress this AR estimation by applying PCA and ICA to separate independent sources and reconstruct this compressed prediction. And if you can learn this pretty quickly, and once you do, at this bottleneck layer, there is information about hidden sources. And you can see that those hidden representation separates 3 and 4 and 2 and 6. They are clusters of 10 digits learned. And we have compared this to different methods, and this predictive PCA and ICA is good. There are reasons to it. So for example, simple PCA is not good. If you apply simple PCA to perform dimensionality reduction of each digit, it can pick up the difference in the strokes or difference in the thickness of the letters as a principal components. But that is not useful for prediction. What is useful is that 1 comes next to 0. And here, the thickness of digit doesn't matter. So you don't want to capture that kind of component. So the PCA per se is not good. And the autoencode is similar thing. AR model tends to overfit the data because it has too many neurons to encode the stimulus. And the state space model, like Kalman filter, is also not optimal because you don't know the underlying system. If you know the model, underlying model, Kalman filter works well. But if you don't know the underlying model, there's uncertainty in the model, uncertainty in the state. So if there's a multiplication of uncertainty in the parameter, uncertainty in the state. That gives a nonlinear uncertainty effect that can give spurious solutions. So the Kalman filter is also not good. So our one can predict both ascending and Fibonacci sequence very well. So here's the test prediction error that decreases with the sample sizes. And because of the simplicity model of the model, it can predict how many neurons are needed at this bottleneck layers. And it just gives this 10 as a dimension of hidden sources. And it asymptotes this blue line. This blue line is with the explicit supervision of hidden representation. If you give that this is 0, this is 1, this is 2, then you get this blue line. But this predictive PCA doesn't use such a label of hidden states, but converge to that performance level. So finally, in summary, we have developed the local ICA and PCA algorithm, irrigated Hebbian rule, that requires only global information sharing by a third plasticity factor. EGHR is suitable for parallel blind source separation and feature extraction by neuromorphic hardware. This EGHR can perform dimensionality reduction by extracting common sources in the multi-context ICA problem. And then we apply that to some nonlinear case. PCA and ICA can blindly separate nonlinearly mapped sources with a asymptotically 0 error, provided many observations and multiple sources. And PredPCA and ICA can identify dynamics of hidden sources and predict sequences. So lastly but not least, I would like to thank a very talented postdoc, Take Isomura, for doing all these works. Thank you.
back beyond that.
Mm.
No.
Huh?
The
This one?
last one before the conclusion.
That's one before the conclusion. Yeah.
Okay. So there's a couple things I don't understand,
Mm.
but in that graph at the bottom that compares the performance of the different ones.
Yeah.
There's one of those
this
which
one,
does
this one.
almost as well as yours, and which is
Oh, this one. This is the Kalman filter plus ICA.
plus ICA.
Yeah.
Thank you. And on the error graph, it seems the asymptote is almost 50%. Why is it that high?
This is because there are some errors. It's not purely deterministic sequence. Sometimes random digit is assigned, or sometimes we also flip the black and white, so that gives additional noise.
Okay, so you're doing this in a very noisy environment. Suppose it was less noisy, then could you just move that floor down?
I think so. But another difficulty is the variability of hand digit sequences. Sometimes you receive very weird 7, which is almost like 1. So that is harder to distinguish. So there are that's an additional noise source.
So these are all from MNIST?
MNIST, yes.
Sorry, I have the microphone. Hey, I wanted to ask with the third factor learning rule. I always wondered, like, you use this third factor for the weight update, right? But you don't use it for the dynamics itself. So it's not influencing the firing rate of the post.
That's right.
Synaptic fire.
That's right.
And like how, for example, if you have the GABA, are there attempts to, because I imagine it might also influence the postsynaptic firing rate maybe itself, or are there, are people looking at this, or I don't know?
Well, definitively there is an effect on plasticity rule. Let's say Haruo Kasai and others show that depending on the GABA level, learning rule can be different in the experimental setup. But you're right that inhibition in general can change the activity level. So I don't know, maybe there are multiple kinds of neuromodulators or inhibitions, some targeting activity, some targeting plasticity that I don't know. At this point it's a proof of principle. If you have this kind of signal, you can do interesting stuff. But I think hypothesis like this is useful because given the task, we can theoretically compute this error factor and see if you have a correlated signal and experimental observations or fMRI or something like that can be done once we can formally write down this error factor. But you're right. Inhibition can change activity, but let's see if there are diversity of inhibition, for example, and if they do different things.
Thanks.
So this is a comment. So there is this work that they applied PCA on place cells, and then they don't get grid cells. But if they apply PCA, which is how to say threshold at positive this PCA, then they get grid cells. It's a paper by Dori Derdikman, and I never understood the biological basis of that kind of thresholding, but I'm wondering whether this thing can be applied to something like place cell data to see whether I guess
if the transformation from place to output is linear, then it's much easier. But I guess you were talking about the nonlinear case.
Yes, yes.
Even in some nonlinear case, you could do extract the sources by PCA. I mean, I don't know. I mean, whether this is directly applicable in that situation. First of all, we assume that there are multiple sources. It doesn't have to be infinity, but let's say 10 sources, order 10 sources is needed to sort of to be able to linearize. So this theorem can hold even when this nonlinearity is like a step function, jumping function. It's okay because there are other sources of variability which effectively linearize discontinuous function. So for this to apply to arbitrary kinds of nonlinearity, you need multiple sources. In the place exploration task, I don't know what's the true dimensionality of hidden sources. I mean, if it's a 1D track, maybe it's a 1D. Who knows what's the...
Yeah, but I mean, I think people tend to think that it's a two-dimensional thing, but I really don't think so. I mean, there is also some new stuff by David Tank's lab that shows that there is more dimensions to the...
Yeah, another, so here we're talking about sort of, many sources equally contributing to the activity. So if one is strongly dominating the output and others are negligible, then it doesn't hold. And also, you need multiple outputs projecting the activity to different directions. So that's a requirement for this to be the case. So I don't know. I mean, maybe it's applicable to the place cell case in some cases. Yeah, I think it's interesting, but I don't know if it holds.
Thank you.
So going back to the last example, so I was wondering if are you learning the two sequences at the same time, or?
No, one at a time.
One at a time.
Yeah.
And so why does the Kalman filter do less well for the Fibonacci sequence than for the ascending?
Oh, it's the complexity of the model space. To predict Fibonacci, you need the higher dimension of states, because you need to combine the past 2 digits to predict the next. So the state becomes higher dimensional, and presumably there are more nonlinear uncertainties. I said uncertainty of parameters multiplied to the uncertainty of state can do bad cause error, and that's probably happening more in a high-dimensional state space with a Fibonacci, I suppose.
It's more like a comment. I can understand the wish to minimize energy consumption when you have to design an artificial device, a computer, and so. However, using energy consumption and as a biological constraint for brain is not. There's no, shall we say, in vivo studies supporting the so-called energy budget. The energy budget comes from some articles by David Atwell and Simon Laughlin 25 years ago, and they were made on slices. And the calculations of the cost of the action potential is probably wrong. So actually, it's the other way around. When neurons are working very fast, there is an increase in blood supply and glucose, and the diffusion path to the neurons gets much smaller. In addition, also, the oxygen tension next to the neuron increases. So there is an oversupply of energy even when the system is challenged, such as under an epileptic fit, for example. So there is no reason to use, shall we say, energy consumption constraints when you design models of the brain.
Yeah, well, I appreciate that there's a heavy debate going on there, but let's say if you observe fMRI for common situations, neurons aren't, or both signals aren't that active, and if you are exposed to novel conditions, suddenly a vast majority of areas start to respond. So there seems to be some kind of sparse coding still in the brain. I mean, whether energy per se is the best constraint or not is a question, but I think, still a sparse representation is preferred in a natural environment.
I don't think you should take fMRI as a good indicator of what goes on in the neurons. It takes about 800 milliseconds to produce an fMRI fMRI signal. So, so what I'm saying is that there's no in vivo measurements supporting the energy budget. No in vivo.
Okay,
and that has to be made very fast, right? And also, it's debatable how sparse the coding actually is. Depending on the method you use, if you use very fast methods to look at membrane potential and changes in membrane potential, there's vast areas of the cortex being depolarized. And so there is certainly something to discuss here, I think.
Okay, yeah, sure. Thank you.
So I have a question on this EGHR. Well, the question is, it looks like a strategy that you could also apply in artificial neural networks.
Mm-hmm.
And then the issue is how well it generalizes. So how well it performs in generalization. Because what it seems is that since you are mapping a function, you are minimizing a function which is, when you get this energy equal to 0, then your dynamics stops, essentially.
Mm-hmm.
So it looks like the locus of stationary points is very high dimensional. And so maybe there are many. So the question of how well it generalizes, I think it's something that one should
sure. So you're talking about one thing is whether there are a spurious solution, local minima in the energy or error function or not. And another question is, suppose you are near to the solution, how quickly you converge to a true minima with the final sample.
It's clear.
Second one. Yeah. The second one is about the efficiency.
No,
right?
the second one is clear. The first one is
the first one.
How degenerate is the minimum?
Right. I mean, how many minima are there? I think that's
it's a quadratic function, so there is only one minimum. But the issue is how degenerate it is.
It's a quadratic function of the error, but it's not the quadratic function of the weights.
No, of course.
So I guess what we learn is synaptic weights, and what is the landscape of the weights is also an issue, I think. We don't have any theoretical proof about that. No, I mean, we can prove that as if the source distribution is approaching Gaussian, then there will be no spurious solutions. That's a theoretical result. And we also numerically explored up to 10 or 20 dimensions if there is any signature of spurious solutions. When we explored a good condition like IID sources, then there was no signature of local minima, but it's not a mathematical proof. So
Yeah, no,
I think it's
discuss offline. I mean, there is no local minimum. It's just there is one minimum, and it's very degenerate. So that's my point.
it's not degenerated to our numerical exploration. Sure. Thank you.